ladies and gentlemen, good afternoon. My name is Prince. So, my presentation this afternoon will be focusing on balancing of electrical loads. Now, this presentation was brought to you by the Digital Society of Engineers. We're an online engineering platform that creates network opportunity for electricians, technicians, and engineers working in the field. All right. So we make it easy for persons to dialogue within the field and share ideas and experience and so forth. So we're going to be explaining load balancing, what it really is, how we achieve it, and how we go about doing our calculation as regards balancing electrical loads. Now, what is electrical load balancing, right? And how is it important? Now, electrical system is required to have proper distribution of the loads to achieve a safe outcome. Now, safety is important, and it helps us to prevent any hazard in regarding electrical systems, right? So the important roles of proper balancing is to have the load distributed safely, right, on the electrical panel. And the electrical distributed system, of course, it carries two or more phases. Electrical loads distributed throughout the network is very important that a reliable electrical system is maintained. Now, the primary reason for maintaining the balance of loads on the electrical distributed network is to avoid overloading on one side of the panel. Can you imagine stacking up all the loads on one panel, and it will create a condition for failure on the electrical system because it would basically be carrying too much capacity on one side, causing a major burn down. So the primary reason for maintaining the balance of the load on an electrical distributed network is to avoid overloading on one side of the panel. All right. So the other reason is to ensure that the difference in the line current from all phases of the system reduces the magnitude of current on the neutral to the lowest value, hence preventing overheating on the neutral and creating a brownout of the neutral. All right. So you want to have a differential in between phases. So whenever you have a return on the neutral, the value is so small that it can't really create a conditions of burned out. All right. So balancing on electrical system helps us to understand how the current flows in the system. Now we may balance the load in some system, while in other system that is a no-no because there can be a balance situation can only occur when there's a three-wired system from a two-phase network, right? Some cases we may call that single phase as well because we don't consider two-phase to be more than just a single phase, right? So we have to try and create balance situation. We have like a three wires, single phase or two-phase network, right? So for the two-wire circuit though, it is quite unique. Most we consider this the branch circuit, right? And this is fed from one side of a electrical panel. Right? There's cases where you have two-wired circuit feed into households. All right. So when there's a two-wire situation, the current flowing in the neutral of a two-wire circuit is just as the same as the current flowing in the ungrounded conductor. So what is flowed out from the ungrounded conductor is returned back onto your neutral. The three wires 12240 single phase circuit. The current flowing in the neutral of the three wires 12244 single phase circuit equals the difference in the current flowing in the ungrounded conductor. Right? So the three wire 12240 single phase will carry two phases, maybe line 1 and 2 or 2 or 3, right? Some cases, the three wires derived from the four wire circuits. All right, so the difference in the two lines is going to result in your neutral, right? So the difference, the reason for the difference is that the two ungrounded conductor opposes each other. So note if the ungrounded conductor of the multi-wire branch circuit are incorrectly terminated, so there is no difference between them. The ungrounded conductor will cancel out on the neutral conductor. So this may cause the neutral to be in excess of its capacity and hence cause a burned out. Right? So you incorrectly terminated the two wires in such a way that they heads up. Then the ampacity would definitely spike up and it will return back to the neutral excess of in an excess amount and it will cause the burden out to the neutral. So we have to be careful how we terminating these wires that they don't create a situation where the value becomes much of greater than the value of the neutral, right? Resulted in the conductor being burned out, right? So the balance system now. So if the current carrying conductors of a multi-wire branch circuit is the same, the neutral conductor will carry zero amps. This applies to three wires, 120, 240, single phase, and all the three phase circuit, regardless of configuration or voltage. All right, so the balance system is just that system that have the same loads on both phases. So the system actually neutralizes and the current returning on your neutral would be 0 amps. All right. So in a unbalanced situation, however, the current flowing in the neutral would not be zero because the current or because the differential of the loads is just not the same. All right. So the current flowing on the return or the neutral is not going to be equal to zero. So careful consideration must be taken into account when you have an unbalanced system. Now, three wires, 120, 240 volt single phase circuit. The neutral conductor of a three wire 120, 240 volts circuit will carry current only when the ungrounded conductor don't have identical current flow. All right. So the unbalanced current is the difference between line one and line two. All right. So when the conductor of the ungrounded side is not identical, then you will have a current definitely flow on the circuit. All right. So that's what makes the circuit unbalanced. Right. So once you have a differential between both lines, then you have a current flow, and that's what is returned onto your neutral. The next thing now, a three-wire circuit may derive from a four-wire three-phase system. All right, that is the one we talk about having a three-phase system and then taking like a single-phase circuit from that system. All right, that is the same as a two-phase circuit, a two-phase system. Right, so we're taking only maybe line one and line two or line three or line two and three and so forth. Whichever, only two taken from the four wire three phase system where it consists of phase one, two, three, and a neutral. All right, so let's say the neutral conductor of a three wires 120, 240 volt, 208 volts or 277 slash 408 volts three phase circuit derives from a four wire three phase system will carry a neutral. All right, so this system at some time will be unbalanced. That's basically what they're saying. That you may look for it or look forward rather to a current flow within the system when the system is not carrying a balanced load. Now, for four-wire three-phase system, four-wire circuit from a four-wire three-phase system will all also produce a neutral current when the loads are not balanced. All right. So we just mentioned that the load would have to balance in order for no current to flow. But because sometimes there's going to be an unbalanced situation, then you'll have current flow within the system. So the critical thing that we try to achieve from balancing is to prevent a current from being flown into the neutral, right? We would say it's impossible to avoid that kind of situation because of the unideal conditions of most electrical systems. All right, but if we can reduce the value to that which is minimal, then of course, that is something we want to achieve. All right, so that is the fundamental importance of deriving a balance system. All right, so when we calculating the neutral current in the three-phase system, all we have to do is add up, say, the square of L1, L2, and L3, and then take the difference of the product of L1, L2 times L3, right? All square rooted. So when we work when we work out this value now, it should give us the maximum current that is going to flow within the neutral, right? Either when line 1 is 0 or line 3 is 0 and L1 or line 1 is at its max. All right. We may also calculate the neutral within the three wire, right? Three wire system. Remember, we talk about the four wire three phase system and the three wire three phase system. That is when I know the three wire system is when ideally one of the lines is not available. All right, or one is not being taken out from the four wire system. So the three phase system where L3 may not use, or one not use, or three, or two not use, and so forth. So we can find a neutral by taking the square of L1 plus L2 minus the product of L1 times L2 and divided that by the root or square root. All right, so the three wire derived from a three phase system. So where the three wires derived from a three phase system, right? The current in the neutral is equal to L1 minus L2. All right, so the maximum current value is attained when the current in L1 is at max, or the current in L2 is 0, or vice versa, where I2 or L2 current is at max and I1 is equal to 0. All right, so the current that is going to return within the neutral is going to be the difference between L1 and L2. However, at max, where there's a failure on the first phase or the second phase, then the current that is going to return is going to be the maximum on either line, maybe line 1 or line 2. That's why we said the maximum current value is attained when L1 is max, or L2 is minimum or 0, or L2 is at max and I1 or L1 is at 0. So either one of the line is being taken out. So the return current going back to neutral will be at max. All right. So the maximum amount of current that is derived from a neutral is when one of the lines is filled and the current return back to that neutral is at max. So the current on that, or the conductor rather, for the neutral should be able to withstand the return current. Now question. So balancing, if you should balance a load and determine the load and the neutral in ampere from these given appliances. So we have 3000 VA, 1020 volts small appliances, 1500 VA for 120 volts larger circuit, 1800 VA for 120 volts dishwasher, 2000 VA for 240 dryer, 1500 VA for 120 volts disposer, right? So note the load 2000 VA doesn't affect the load balancing as it creates no current on the neutral. All right, so let's look at the phases. So we have phase one and phase two. So we put loads on phase one, 3000 VA, 1500 VA, phase two, 1500 VA, and 1800 VA. So that is all taken out from the appliances loads that is given in the power step. There's only one load in particular that is being ignored, which is the load 2000 VA for the dry. All right. So the reason why we're taking out that load is because that would not affect our load situation or our neutral rather. If we're asked to calculate the neutral current on the system. All right. Remember the main purpose why we calculate for neutral current is to create a balanced situation between the two phases. All right. So after we balance the following loads or the loads, then we're going to determine the amount of current flowing into your neutral. All right, so we're balancing it now. So we're taking one set of load on one side and the other on the other. Right, so we try to make it as minimum as possible where the current is concerned between L1 and L2. Right, so we distributed our loads evenly on both phases, maybe from a distributed panel, right, and so forth. So the neutral current, right, is now the current between L1 and L2, right? So that's how we determine the current within our neutral. So this now is going to be the minimum current that is going to obtain rather from the differential after the load balancing actually take place, right? So that is actually 10 amps. Now the next question we're going to focus on is we have we have we call it now fluorescent lighting and supplied by two different circuits, right? We got to determine. So the question it says, what is the neutral current for the two 16 amps 120 volt circuit with a common neutral, right? So the system is 120 to 208 volts, three phase, four wire, Y connected system that supplies fluorescent lighting, right? So what we did for this question is that we considered two phases, right? So we had two different circuits on the different phases for the three phase four wire circuit, right? Now we use a formula where we take I n or the I neutral equated to the root of L1 plus L2 plus L3 all squared minus the difference of L1 times L2 times L3 all squared. All right, so if we can go back to previous formula that we use, now this would give us now a differences as we calculate, and then after taking the root to roughly 16 amps. All right, so this is just standard requirement as it goes to calculating the maximum amount of neutral current that can possibly flow within a circuit, right? We can also use the next formula where we said I neutral is equal to the difference between all the three phase or the phase, all right? But this formula will apply to the three-phase system. It also can apply to two-phase system as well, otherwise called the three wires um, system. So there's a general formula which is used for calculating neutral within, the three-phase system. All right, even if two phases is taken out from that system. So this formula is what we use here to obtain the value of the neutral current. All right. So because this three phase is considered, we only use two phases within the circuit for this electrical what you gonna call it, fluorescent lighting um, circuits, right? Each of them produced from 200 producing from a 16 amp supply. So we work out that to be 16 amps, right? Remember I said if L1 is equal to maximum 16 amps or L2 is actually 0, then what is returned is going to be the maximum that is on L1 or L2 or vice versa. All right. So we could have used a simple formula rather than go in depth with this formula here, which is a little more, complicated nonsense. All right. So the next one we're going to look at is balancing. After balancing the following loads. All right. So we're given some loads in this question here. Um, we're going to find the maximum neutral current. So we have three 1900 120 volts lighting loads and two horsepower 115 volts motor. All right. So we have roughly five different loads in questions. All right. And we're going to balance them or distribute them on our electrical panel or distribution system. All right. So phase one, we have three 1900 VA lighting loads, and phase two designate two horsepower motor load. The value as calculated for the motor load is 2760 VA. All right, so when we take in these values in account, we works out a value of 46 amps on phase two and a value of 47 amps in phase one. All right, how we get that value is basically dividing the voltage value of each phase, which is 120 volts. All right, so we add up all the loads, phase one and phase two, and then we divide that by 120 volts. All right, so the maximum current in I1, or the neutral rather, will occur when either phase is at max and one is taken out. All right, so L2 is 0 or I2 is 0, and where L1 is at max, right, 47.5 amps. All right, so from the two phases, when we calculate the loads, we get one 47.5, the other 46 amps. So we said the maximum amount of current that will flow in the neutral is either when I1 or L1 is at max and I2 and L2 is 0. All right. So the value of the neutral current that is going to return is going to be 47.5 amps. And it can also be calculated using the formula that was given earlier. And that is where we're taking the neutral to be equal to the root of L1 square plus L2 square minus L1 times L2, right? And if we plug in these values, all right, then would have also get roughly 47 amps, all right? So you can consider doing it two ways rather than one, okay? But within a three-phase system, this formula has to be used versus you taking in consideration the value of I max or when one of the current value within the phases is maximum and the other one is minimum or zero. So we're going to just revise this topic, and we're going to go back to what we're coming from. So we said what the idea behind load balancing. So we have balancing of load to have proper distribution of electrical power through the network, therefore thereby making it safe, right, during the operation of the electrical distribution system. And what are we trying to achieve? So first, we want to achieve safety, and then we want to make sure that the value of the current that is returned back on the neutral is relatively, safe enough to operate on the neutral line. All right. So the primary goal in making a kind of arrangement is to, all right, so we are arranging, our breakers, we're arranging switch gears onto maybe a bus bar and so on, a three-phase or single-phase system. We do so in a way that the return or the distribution does not create an hazard situation, because when we terminate our conductors incorrectly, it may adds up more to the value of the return that comes back from our neutral. So we don't want to have that value to be exorbitant, that the neutral would not be able to manage the magnitude of the current that is coming back on it. Remember that is only one neutral, right? Versus multiple phases, right? So all three phases are terminated on at one command point, which is a neutral point, right? From a single phase or two-wired, three-wired system, or a four-wired system, three-phase circuits. All right. So the arrangement should be that when we establish or we laid out our loads, then we would have create a condition where the neutral current would have actually returned to a minimum or zero. All right. So that is the key importance of making the right arrangement. All right. So why are the neutral conductors so important on the electrical system? So the neutral conductor is a part of the electrical circuits. It is what is it's create a part of the functionality of the closed loop operation within each phases of the circuit. All right, within a neutral, you won't be able to have a real say working electrical system. All right, because the load by the line circuit or the line side from where the load is supplied alone cannot operate the electrical system. So you need a return path, and most of the time it comes back to the neutral, right? So the neutral forms a closed loop of the electrical circuits, all right? So that is why it's so important. So because all the system or the phases share the same neutral, a common neutral point, then when we terminate the, the phases, then it should not be that the value or the difference of all the three phases would have produced a value of current that is returning back to the neutral that is so large that the neutral should not be able to attain, or rather handle. Right? So next question is, how does an unbalanced load affect an electrical system? Right. So we getting back from achieving balancing to ensure safety, right? So an unbalanced system basically would have created conditions of failure long term on electrical system. All right. So you want to ensure that your electrical supply or electrical distributed system is of such balance that it does not create any conditions of failure long term by having too much loads on one phases versus the other. So you want to distribute them evenly. So when the current is returned back on your neutral, it is extremely small that the neutral can really handle the amount. Since we said that there's multiple phases and just one neutral. All right. So we balance our loads in order to create a safe system of operation for our electrical circuits. All right. So it's just that simple. So thank you guys for listening on our presentation, and please visit our engineer platform at divisionalsocietyofengineers.com, right, where you can get more information on load balancing on electrical system. All right, so please remember to subscribe to our platform and take the opportunity to share this presentation to a friend. So take care and stay tuned for the next one. Thank you.